Assalamu alaikum and welcome back to our series Fine-Tuning of the Universe. We're now in lecture 9, and in this lecture we're going to talk about the masses of the fundamental particles. But let's just step back and put things in context a little bit. We have just finished talking about the amazing fine-tuning of the initial conditions of the Big Bang, and then from there to prepare ourselves to talk about the constants of nature, we reviewed the very basics of the so-called standard model of particle physics. So I want to remind you, our first series of lectures in this course were about the initial conditions which the Big Bang had to satisfy and how fine-tuned they were. Now, when we're dealing with a law of nature, just to remind you, like Newton's law of gravity, which says that the force between two masses separated by a distance d is given by this formula here. In this formula, g, the gravitational constant of the universe, Newton's gravitational constant, that is a constant of nature. That's a property of the universe. How far apart the masses are, or what the masses actually are they big masses or little masses, those are initial conditions. So we talked about the initial conditions of the Big Bang. Now we would like to start talking about some of the fundamental constants of nature like G. And those fundamental constants include things like the masses of the fundamental particles, charges on the fundamental particles, and the strengths of the fundamental forces that we talked about in the standard model via which these particles interact. So for this lecture, and maybe one more, we'll see how far we get here, we want to talk about the masses of the fundamental particles and how fine-tuned they are and what would happen if they were different. So we, again, just by way of review, have talked about how a nucleus is made of protons and neutrons, and those are held together by the strong force, and they are orbited by electrons. The nucleus is orbited by electrons, and it is the configuration of electrons in the outer shell of an atom which allows the atom to interact or not with other atoms and makes all of the magical chemistry that makes us and all of life possible. So again, the periodic table has 92 naturally occurring elements, and they make up over 60 million compounds. And all of that chemistry is determined by the fact that atoms exist. They can be complex atoms with more than one proton, and they have electrons that then will interact with the electrons of other atoms to make molecules, to form chemical bonds, and that is the basis of life. And again, just to remind us that all of matter, all of these 92 elements, all of these 60 million plus compounds are at heart made up of three fundamental particles: up quarks, down quarks, and electrons. And we talked about how a proton is made up of two up quarks and one down quark, and a neutron is two down quarks and one up quark. So far so good. That's just all review. Now, I want us to remember as well, when we talked about the standard model, that we know that everything is made up of up quarks, down quarks, and electrons. But these are just part of one family. And nature actually has three families, each with four different fundamental particles: up quark, down quark, electron, neutrino. Then another family that has two quarks, the charm and the strange, another electron-like particle, the muon, another neutrino called the muon neutrino, then a third family, top quark, bottom quark, etc. The important thing to remember here is how much the masses of these particles that are in the same group, like the up quark, charm quark, top quark, down quark, strange quark, bottom quark, they vary tremendously. So for example, the up quark and down quark are 4.5 and 9.4 times heavier than the electron, but the other four quarks, the charm, top, strange, bottom, are 190, 24, 95, 8180, and 338,960 times heavier. And in the lepton family, electron, muon, tau, these are the muon is 207 times heavier than the electron. The tau is 3,477 times heavier than the electron. Why they have these values, we don't know. And actually, what's important for us is not these values per se, but that there is a tremendous range, a range of hundreds of thousands of possible values, where the heaviest known fundamental particle, which occurs in nature, let alone things synthesized in a cyclotron, are hundreds of thousands times heavier than the lightest particles. So there's an immense, immense range of possible particle masses that already occur in nature as the fundamental building blocks. And that will become important when we talk about how small a change would be needed to destroy the life-giving properties of the universe. So if a quark could potentially have been 100,000 times heavier than it is, and we say that life becomes impossible if it's twice as heavy, that should give us a feel for how fine-tuned that is, because we really have no idea why it could be a range of 100,000 times heavier than it actually is. Now, what we need to say here is that the proton is a very, very special particle. We talked about how atoms need to have protons, and the number of electrons matches the number of protons. And each of these elements in the periodic table is different than the others because it has a unique number of protons. And so protons turn out to be very special. They are sort of the basis of making the elements. And why are protons so special? Because it is the lightest particle made of 3 quarks. And it turns out that odd numbers of quarks are what make up something called fermions, and they are the group of particles out of which everything is built. And protons are the lightest particle made up of 3 quarks. And in nature, remember, mass equals energy. That's Einstein's law. E equals mc squared. They are interchangeable. And nature likes to be at the lowest possible energy state. And that is why these heavier particles, even though they occur in nature, quickly decay to give up quarks, down quarks, electrons, and so on. So why do they decay? Why would a charm quark decay into something else? Because it is too massive, it has too much energy, and nature likes to be at the lowest energy possible. All of this is building to a point, inshallah. The proton is a little bit lighter than the neutron because the neutron has 2 down quarks, 1 up quark, and down quarks are slightly heavier than up quarks. You could see that here. Up quark is 4.5 times as massive as the electron, down quark 9.4 times as massive as the electron. So down quarks are heavier than up quarks. The neutron has 2, the proton only has 1. So the neutron is heavier than the proton, and it is heavier because up quarks are a little lighter and down quarks are a little heavier. Now, who cares? What if things were a little bit different? You'd say, well, neutrons would weigh a little more, protons a little less, who cares? Well, it turns out that it is actually very, very significant, because even though the neutron mass is only 0.1% greater than the proton mass, nature likes to be at the lowest possible energy state. And so left alone, in isolation, outside of nuclei, neutrons will decay into protons in about 15 minutes. So isolated neutrons are unstable. They are critical for forming atoms, but it turns out that they are stable only in a nucleus when they are mixed together with protons. We'll talk about this a little bit more, but now the takeaway is that even though the mass of the neutron is only 0.1% greater than the proton, left alone, isolated neutrons decay into protons. And this is diagrammed here. This is a so-called Feynman diagram where you see that the way this happens is that a down quark will change into an up quark via the weak force with a W particle and give off an electron and an electron neutrino. It's actually an anti-neutrino to be, more precise. But here is the bottom line. The mass of the neutron is 939.565 MeV, mega electron volts, while that of the proton is 938.272 MeV, very close, being 0.1% heavier, like we said. If the mass of the neutron were only 0.998 that of the proton, if it were 0.002 lighter, if it were 0.2% lighter than the proton, what would that mean? Well, instead of neutrons decaying into protons, now the proton would be the heavier particle, and protons would decay into neutrons. And that would be by a change of only 0.2%. If the neutron, instead of being 0.1% heavier, were 0.2% lighter, now the direction would go like this. This arrow would be reversed. Protons would decay into neutrons. What would happen if protons decayed into neutrons? Well, there would be no chemistry. There would be none of these elements in the periodic table because each of them starts with one proton hydrogen and moves up from there to give us all of the elements. So look at how precise this fine tuning is. The masses of the fundamental particles could have had a range of tens to hundreds of thousands of times what they are. But it turns out that if they were not so precisely balanced, if the neutron were only 0.2% lighter than the proton, protons would be unstable, they would decay into neutrons, there would be no atoms, no life. And so I'm not talking here about a universe capable of supporting life like us. I'm talking about any chemistry whatsoever that would not exist. And here is a long quote. And I know people sort of, shiver when they see this many words on a slide. But I would like us just to go through it together. This is a quote from an article by Paul Davies. And I think it is, again, if we want to understand this stuff, we just have to push a little bit. So don't shudder when you see this many words. And he says, a few numbers do seem to be fundamental to the workings of the universe, however, because they describe the most basic processes of nature. High on this list are the masses of the subatomic particles. Dozens of particles are known to physicists, but the most familiar are the constituents of atoms, electrons, protons, and neutrons. The proton is about 1,836 times as heavy as the electron. Nobody knows why nature picked that particular number. The neutron is very slightly heavier than the proton by about 0.1%. That's really the precise ratio here, according to the best measurements. Why is this? Did the great cosmic designer initially intend the proton and neutron to have the same mass, but they threw in a bit more for the neutron as an afterthought? The neutron-proton mass difference may seem trivial, but it has momentous consequences. Because mass is a form of energy, E equals mc squared. The neutron, as it happens, has a little more mass and thus energy than a proton. And it actually has not only a little more mass than a proton, but then a proton and an electron combined. There is a general principle in nature that physical systems, when left alone, seek out their lowest energy state. That's all what we've been saying before. Sure enough, an isolated neutron will soon, within about 15 minutes on average, spontaneously turn into an electron, a proton, and an antineutrino, as we said, a process known as beta decay. Another particle called an antineutrino is also involved, but that need not concern us here because it's almost massless. The only reason that any neutrons still exist is because within a few minutes after the hot Big Bang that made the universe, some neutrons stuck themselves to protons. And the strong neutron-proton binding force changes the energy balance, not by much, but enough to stabilize the neutrons. So he is making the point that we've already talked about. Isolated neutrons would be unstable. They would decay to protons. We need both neutrons and protons to form atoms. If the neutron were a little bit lighter, all protons would have become neutrons, no neutron. All protons, would have become neutrons, no protons, no chemistry. If the neutrons had not been locked into atoms early after the Big Bang, being stabilized, if they were just left out to drift in the void, they would have all decayed into protons. We would have had no neutrons. And when it came time to make atoms, we wouldn't be able to make any either. So, had the great designer done it the other way around, with protons about 0.1% heavier than neutrons, disaster would ensue. Under these circumstances, isolated protons would turn into neutrons rather than the other way around. And without stable protons, there could be no water and probably no biology. The universe would be very different. The fact that the universe we know, including our own existence within it, hinges so delicately on the precise value of the neutron to proton mass ratio has led to heated debate among scientists. Was it just a lucky fluke that the laws of physics turned out this way, or does it suggest something more profound? Again, Paul Davies, in this article, Why is a Neutron Heavier Than a Proton, from Cosmos Magazine, and he's Regents Professor and Director of the Beyond Center for Fundamental Concepts in Science at the University of Arizona, and a world-famous mathematical physicist. So again, just another citation for you, because when we talk about the neutron, the proton, one being heavier than the other, lighter than the other, remember that all boils down to the masses of the quarks. Down quarks are a little bit heavier than up quarks, so neutrons are a little bit heavier than down quarks. And when scientists model what would happen, what they often talk about is the difference between the mass of the down quark and the up quark, because that's really what's important. And so I just want us to get used to this concept, mass of down quark minus mass of up quark. And Hogan says that detailed considerations suggest that the mass of the down quark minus the up quark is quite finely tuned, in the sense that if it were changed by more than a fraction of its value either way, nuclear astrophysics as we know it would radically change. So let's focus on this notion of either way. We will talk about that a little bit more shortly. But we've already said, if the up quarks were heavier, protons decay into neutrons, no chemistry whatsoever, no elements in the periodic table. Now, he says, on the other hand, small changes in MD minus MU can have surprisingly profound effects on the world through their effect on the relative masses of the proton, neutron, and deuteron. We have not yet talked about the deuteron, but we will. If the mass of the neutron were less than the mass of the proton's unstable and there are no atoms, no chemistry. I know I am reiterating, but I know that this stuff is not intuitive, so I just want to drive it home. It is thus important that the mass of the neutron is bigger than the mass of the proton, but not by too much, since the neutron becomes too unstable. And that's the other direction. Yes, we're happy that the mass of the neutron is bigger than the mass of the proton, because if it were the other way around, protons would decay into neutrons, no periodic table, no chemistry, no life. And we said the neutrons are stabilized inside nuclei, inside atoms. So if a neutron is part of a nucleus held together with some other neutrons and some protons by the strong nuclear force, that changes the energy balance, and an isolated neutron will no longer decay into a proton. But if we make this difference too much, if the mass of the neutron is not just 0.1% heavier than the proton, but is more than that, then even inside a nucleus, the neutron becomes unstable. That favorable energy balance of being bound to protons, stabilizing the neutron, could no longer hold. If the neutron got too heavy, then neutrons inside nuclei would decay into protons, and all of those protons are positively charged. They repel each other too much. Nuclei would burst apart. That's why all elements above hydrogen, other than hydrogen, have to have neutrons in their nuclei. So if the neutrons were a hair lighter, no chemistry. If the neutrons were a hair heavier, no chemistry. So this difference between the down quark and the up quark has to be very finely tuned. And this is what allows atoms to form, like helium, which is 2 protons and 2 neutrons bound together. And the conversion of hydrogen to helium is the reaction that drives the energy of the sun and on which all life depends. Now, why 2 protons and 2 neutrons? We already talked about it. If it was 2 protons alone, they would repel each other. If the neutrons inside atoms were too unstable and they changed into protons, now we'd have 4 protons, and that's what would happen if the neutrons were heavier than they actually are, and the nucleus would fly apart. 1 neutron, 1 proton, that's the deuteron, and it is the first step of hydrogen, which is just 1 proton, no neutrons, becoming helium. Hydrogen joins with a neutron, the proton joins with a neutron to form a deuteron, 2 deuterons join together to make helium. And that is stable. So this is what we have then. Let's look at this graph that shows us how much the world depends, the universe really depends on the balance as it exists between the mass of the down quark minus the up quark. That's this quantity we talked about here, and we said we wanted to get familiar with this scale, mass of down quark minus mass of up quark. So I want us to look at this scale. We're talking about just a few electron volts. And on this scale, this is the only area that would permit life. We're talking about the electron mass going from 0 to 4 MeV. The electron mass as it exists is actually about 0.511 MeV. And if we go up, that's where our universe is, with an electron of 0.511 MeV. And the difference between the down quark and up quark mass is around here. That's where our universe is. So we've already talked about, but now let's try to understand it in terms of this graph. What if the down quark were much heavier than the up quark? That difference would be bigger. We'd move up. Instead of here, we'd be somewhere up here. We've already said if the down quarks were significantly heavier than up quarks, then neutrons would be much heavier than they actually are. And it actually doesn't take much, just a little bit. Neutrons would be a little bit heavier than they are. What would happen then? Even inside atoms, they would decay. They would decay into protons. There would be no atoms. And the only thing left would be proton world. What if the difference were less? like for example, the up quarks were just a bit heavier than they are. If the up quarks were a bit heavier than they are, then what would happen is that the proton would get a little bit heavier, it would decay into neutrons, and we would be in neutron world. If the electron were a little bit more massive than it is, protons would capture electrons, turn into neutrons, and again, we would be in neutron world. So it is only in this little triangle where our universe sits that we avoid being in a world that is just protons or just neutrons with no atoms, no chemistry, no life. Now you may think, well, this triangle is a pretty sizable piece of this square. That's why I wanted to call your attention to the scale. We're talking here about only a few mega electron volts. This is just about 8 times what the mass of the actual electron is. This is just a couple of times what the difference, even less than a couple of times, what the difference is between the down quark and the up quark. And when we talked about all of the range of masses of the particles, the charm quark, the top quark, the bottom quark, the strange quark, those go up to gigavolts. So this scale of 4 mega electron volts is nothing compared to the range of particles that we know exist, of the fundamental families. If we were to make this graph to scale, to the scale of the masses of those fundamental particles, this little triangle, instead of sitting in a square this big, would sit in a square that is 10,000 acres. So imagine that you go to a plot of land that is 10,000 acres, and the only part of it that would permit chemistry and life in a universe was this small. This triangle wouldn't change size. It's just instead of being in this block, it would be in a block that is 10,000 acres in area. And if instead we were to go to the particles that have been created in the lab, so we know that they can exist, although they are not part of the 3 fundamental families, it would be this little square and something the size of Switzerland. So that should give us an idea of how precise this fine-tuning is, how exactly, as Paul Davies says, the cosmic designer had to pick these values. If they go change by 1 way, then we're in proton world, only protons, no atoms. If they go the other way, then we're in neutron world. Again, no atoms, no chemistry. So now I want to make this point a little bit more finely, but it's still the same point. But I want to show you this really complex graph, and it comes from a paper by Luke Barnes. And this is looking at the natural log of the mass of the down quark compared to the Planck mass, mass of the up quark compared to the Planck mass. So the range of possible values that the down quark and the up quark could have had. Our universe sits here. This range, this is a logarithmic scale, and it spans orders of magnitude that is more than 100 orders of magnitude. If we just talk about 60 orders of magnitude, 60 orders of magnitude means things could have been a trillion, 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 trillion times what they are. So imagine that this is not a logarithmic scale, and we are talking about 60 orders of magnitude on the possibilities. Our universe sits in this square, and it's on this dot. Now, if we were to blow up this dot and look at just those orders of magnitude, our universe sits right there, and it is this green triangular shape where any life at all, any chemistry at all would be possible. And each of these curves imposes a very serious sort of constraint, where no chemistry as we know it would be possible. And it is only in between all of those constraints in this little green triangle that life would be possible, and our universe is one dot within this triangle. And again, this is within a space of tens of thousands of possibilities. That's the order of magnitude. And so the fact that we can exist within this little triangle, if this were not drawn on a logarithmic scale, you would again be looking at something, say, the size of Texas, just to spitball. And this little triangle would be sitting in the middle of Texas, and within it are our universe, this tiny little triangle. That's the only space of possibilities where life could exist. So what are all these lines? Well, we don't have time to go through all of them, but above this blue line, this would mean that the down quarks are really quite heavy. And so if down quarks are so heavy, instead of having 2 down quarks and 1 up quark in a neutron, the down quarks would be so heavy that they would all want to change into up quarks. Why can't we have 3 up quarks? Well, the reason we don't normally have that is because they're all positively charged, they would repel each other. But if the down quarks were so heavy, it would still be energetically better to have 3 up quarks. Do we know a particle that is made up of 3 up quarks? We said proton is 2 up quarks, 1 down, neutron is 2 down, 1 up. What about 3 up quarks? Well, such a particle is experimentally possible. It is known as a delta plus particle. So if we are above this blue line, down quarks are so heavy, the entire universe would have just been delta plus particles, no possible chemistry whatsoever. So we would have to be below this blue line, but that's pretty extreme. Down quarks have to be pretty heavy for that to happen. What about curve number 2? Well, if we're above the red line, the deuteron, we talked about how a deuteron is critically important because hydrogen joins with, a proton joins with a neutron, the proton and hydrogen joins with a neutron to make a deuteron, and 2 deuterons join to make helium, and that is how the sun burns hydrogen. The deuteron would be highly unstable, and it would decay through the strong force. And so the first step in so-called stellar nucleosynthesis, the first step in the sun burning hydrogen to helium would be gone. And remember, all of the elements that make us up pretty much are synthesized inside stars. So stars wouldn't burn, and they wouldn't make the complex elements that make us up. So we would have to be below this red curve, because above the red curve, deuterons would be unstable. Now let's look at the green curve, number 3 here. Above the green curve, neutrons within nuclei decay. We've already talked about this. If the neutrons were just a little bit heavier, they would decay, and we would be in proton world. Okay, and again, that's if we go up on this side of the mass of the down quarks. If the mass of the down quarks were a little bit higher above the green curve, neutrons within atoms would decay, and so no atoms would be possible because atoms need both protons and neutrons except for hydrogen. So we would have to be below the green curve. And you can see that as we go through all of these different constraints, it will eventually boil down to that life is only possible in this little green triangle. So let's, for example, look at curve number 4. Below the red curve here, the diproton would be stable. Remember, we talked about how in nature, 2 protons being together is not a stable arrangement. We want 1 proton, 1 neutron that's stable. What if the masses of the down quarks were low enough that 2 protons became stable? This is known as the diproton disaster. And two hydrogens would fuse together to make helium-2. And this is a very fast reaction. The sun would burn through its fuel at an astronomically fast pace, and no life as we know it would have a chance to develop. There would be no stability of the stars. So that's what would happen if we were below curve 4. Let's look at curve 5. Above curve 5, what would end up happening is that if you were to try to produce deuterium in stars to produce deuterons, instead of that producing the energy that powers stars, it would absorb energy. So that would be a problem. Stars wouldn't burn. We can't be above curve 5. We have to be below curve 5. Now let's look at curve 6, and then we'll stop there. So below curve 6, what would end up happening is that protons in a nucleus would capture orbiting electrons and become neutrons. The mass of the down quark is low. If we're below curve 6, the mass of the down quark is low, and we've already talked about what happens when the mass of the down quark is too low. What ends up happening is that protons change into neutrons. And one way they can do that is that the protons absorb electrons. And it turns out that if the mass of the down quark, from the tens of thousands of possible values that it could have had, the tens of thousands of orders of magnitude that it could have had, is only 8% lighter, protons would capture electrons. So if the mass of the down quark were 8% lighter than it is, protons would capture the electrons that are orbiting them in atoms. They would turn into neutrons, and we could have no chemistry. So we can't be below curve 6. We have to be above curve 6. We have to be below curve 5. We have to be above curve 4. And so you can see how those constrain the possible values of the mass of the up quark and the down quark. I know I've talked a lot. I know this was probably way more detail than you were interested in. But remember, this little area is sitting in a logarithmic scale curve. If you were to draw this curve to scale, it would be the same phenomena we talked about here. Life would be possible on this very tiny little island in an ocean, say the size of Texas. That would be it. That's how finely tuned these masses of the fundamental particles are. Now, I said, I know I've talked too much. Probably say, this is way beyond what I ever wanted to know, but I'm hoping there will be a few of you out there that will say, no, this is really neat. I'm so interested. What about curve 7, 8, 9? What's happening there? Well, this diagram actually comes from this paper by Stephen Barr and Almas Khan. They are at the University of Delaware. Stephen Barr has written a wonderful book that is called Ancient Faith and Modern Physics, or Modern Physics and Ancient Faith. I think that's the title. I've actually read the book a couple of different times. It is phenomenal. He is a particle physicist. This is the paper if you want to look it up, but I just want to give you an alert that you need to know a reasonable bit about particle physics, about quantum field theory for this paper to make sense, but they are the ones who calculated these curves. So with that, let me then stop here. I hope I've driven the point home that the masses of the fundamental particles are exquisitely finely tuned. And if they were different than they are, and we don't know why they are the way they are, we don't know why nature picked these ranges, but we know that there is a big range to choose from the particles we already know exist. And if they were just a hair different, no life could exist in the universe. So I hope I have made my case for fine-tuning of the masses of the fundamental particles. And that, of course, is just one part of the story of the constants of nature. Next time, inshallah, we will talk about the forces of nature, the forces that make those particles interact with each other, and see that not only are the masses finely tuned, but the forces are finely tuned, and you get the idea that if we have to fine tune the forces, we have to fine tune the masses, we have to fine tune the initial conditions, it becomes pretty hard to believe that this is all just one accident. So I will stop the recording here. I hope you've enjoyed it. Take care, God bless, and I hope, inshallah, you will join us for the next episode. Salam alaikum.